Software engineers constantly face the challenge of taking raw, chaotic data and organizing it efficiently within the strict memory boundaries of a system. Historically, setting up standard, pre-filled lists to hold this data required a highly verbose, multi-line process. You had to first instantiate an empty list object and then manually append each element, line by line, until the entire structure was finally populated. This legacy approach carries a hidden architectural risk. These standard lists remain inherently mutable, meaning the data is left vulnerable to unintended modifications later in the execution cycle. This older method prioritizes absolute structural flexibility at the cost of systemic security and code conciseness. To address this, Java Development Kit 9, or JDK 9, introduced a modern solution, the List.of factory method. This specific factory method takes that verbose legacy process and condenses it down into a single clean line of executable syntax. You simply call List.of, passing in the exact string elements you need, like A, B, and C, right at the moment of creation. Many developers assume the method merely acts as syntactic sugar, a simpler way to generate the exact same standard list they are used to. That assumption is incorrect. List.of does not return a standard list, but a highly specialized, rigidly restricted implementation managed by the JVM. The JVM, or Java Virtual Machine, is the engine that executes the code and manages system memory. Utilizing this modern method binds you to a strict architectural contract hidden beneath that simple syntax. The first absolute invariant of this specialized implementation is strict null hostility. Attempting to pass a null or completely empty value into this specific list structure is prohibited by the JVM. If standard data blocks enter, the list accepts them smoothly. But if a null value approaches the intake, it shatters upon contact. The system immediately rejects the null value by throwing a fatal null pointer exception. A null pointer exception is an error thrown when an application attempts to use an object reference that has not been initialized. This restriction exists because null values complicate mathematical predictability within system memory. When standard lists allow nulls, the JVM must execute processing-heavy edge case checks during every read operation to ensure it isn't encountering an empty reference. By categorically banning nulls, the implementation removes the need for these continuous parasitic safety checks. Null hostility is a deliberate subtraction of complexity designed to enable higher baseline operational speed. The second strict invariant enforced by this factory method is that the resulting list is non-modifiable. In this strict context, non-modifiable means internal elements cannot be added, removed, or replaced after the list is created. Once the data populates the array, the list transitions into a permanently locked state to repel any external modification attempts. Calling methods like .add or .set instantly triggers an unsupported operation exception. An unsupported operation exception is a specific error indicating that the requested operation is not supported by the underlying class. This differs from standard dynamic arrays, which must perpetually leave memory space open for future additions. A dynamic array must negotiate with heap memory to expand its boundaries as new data arrives. Heap memory is the portion of memory allocated to the JVM where all class instances and arrays are stored at runtime. Enforcing strict immutability fixes the data structure's exact footprint, eliminating the resource cost of dynamic memory resizing. The true engineering payoff occurs when the strict null barrier and the immutability padlock act in perfect synchronization. Because the JVM guarantees the list's size and contents will never change, it executes specific structural optimizations that are impossible with standard lists. We see this in the system heap, where the list elements are tightly packed into a continuous memory block without empty padding. This packing reduces the specialized data structure's overall memory footprint compared to dynamic lists. This continuous layout allows for exceptionally fast, unimpeded read operations across the entire structure. Because the state cannot mutate, the list is also inherently thread-safe. Thread-safe means multiple processing threads can access the list simultaneously without data corruption. These specialized implementations are also inherently serializable. Serializable means the object can be converted into a byte stream to be saved to disk or transmitted across a network. Serializability ensures this optimized state can be reliably flattened and transmitted flawlessly between different systems. The strict developer-facing invariants exist solely to enable this hyper-optimized, intrinsically secure, and exceptionally fast internal architecture. Stepping back from the isolated list structure shows its place within the broader Java ecosystem. This entire architectural paradigm was introduced in JDK9 under the feature Convenience Factory Methods for Collections. The objective was to standardize this optimized, immutable approach across multiple core data structures. This standard applies beyond lists, including set.of and map.of. There is an exact equivalent convenience factory method designed specifically for instantiating prefilled sets. This equivalent optimized method also extends to maps, even if the feature name doesn't explicitly mention them. These set and map variants inherit the same functional constraints, absolute null hostility and rigid non-modifiability. JDK9 deployed a unified, ecosystem-wide framework for immutable collection instantiation. Understanding the difference between developer syntax and system architecture clarifies the value of these tools. Executing a List.of command is an architectural decision that dictates how data behaves in memory. It rests on 4 core pillars. The implementation is null-hostile, non-modifiable, optimized, and serializable. When choosing this method, you actively consent to these strict structural invariants. Utilizing it without respecting them results in severe application-breaking runtime exceptions. In exchange for structural rigidity, the developer leverages the maximum optimization power of the modern JVM. Utilizing List.of is an architectural choice, where deliberate immutability results in systemic efficiency.